The prior talks have covered the experimental studies of the many electron problem, and now we're going to turn to two theory talks to round out the session. That gives the next two speakers an easy job. They just have to explain everything we just heard about. So the first person who will attempt to do that is Steve Kivelson. He's a professor of physics at Stanford. He's made broad contributions to many areas of theoretical condensed matter physics, including one-dimensional electron systems, the theory of glasses, of course, high-temperature superconductivity, and quantum Hall effects. He's really particularly known as an eloquent and compelling speaker and researcher who's able to extract the essence of experiment and use it to guide theoretical studies. So he makes an excellent choice for the segue here to theory. He's a Sloan and Guggenheim Fellow and a Fellow of the National Academy. He'll be telling us about theoretical approaches to correlated electron problems. So, Steve.
Thank you. According to Jim's criteria, I'm allowed to be angry at him. He showed all my favorite trees, but I have to talk. And not only that, I have to follow one of the most beautiful and clear and interesting talks I've ever heard. I was also somewhat daunted by this challenge of what to say. And as I thought about saying broad and visionary things, I realized that if I do that, there will be no content. So what I'm going to do is first spend a minute apologizing for the narrowness of what I'm going to talk about, and then try to explain at least one thing where I think considerable theoretical progress has been made in the last several years. So to the extent that I'm describing work of mine, it's been done in collaboration with a large number of people, but in particular, this cast of characters here and various others. So first, let me discuss very briefly some of the really exciting developments that have occurred in the theory of correlated electrons in the last few years that, for lack of time, I won't discuss. So, but which nonetheless certainly represent great advances in the field. So the first, which Laura already mentioned, is there have been enormous advances in what I would call practical approaches to the strongly correlated electron problem, things that, for instance, combine the MFT or functional renormalization group with realistic band structure calculations. So what I'm instead going to talk about is theoretically well-controlled approaches to, unfortunately, very simplified model problems. There's been really exciting and transformative progress in the theoretical discovery of all sorts of fascinating new quantum phases of matter. I find this area extremely exciting, but I won't say anything about it except to mention a bit about one exotic phase, which is not nearly as exotic as a spin liquid, but has some rather unusual broken symmetries. This field of many-body localization is clearly something that is leading to great new insights. Bringing insights from neighboring fields of string theory into condensed matter physics is something that's, again, very promising. And finally, there's been enormous progress in numerical methods for studying many-body systems, which fortunately will be covered by the next speaker. So what I'm going to do is talk about progress that's been made in solving some simple paradigmatic models, in particular the Hubbard and TJ models. Now, as I thought about this, I could hear my friend Chandra Varma telling me that the Hubbard model is shit, that it's not the model of any real material. And of course, he's right. And so, on the other hand, my answer to that is that the Hubbard model really has been the paradigmatic model in which the theory of this of strongly correlated systems is discussed. It plays the same conceptual role in the theory of correlated systems that the Ising model did a generation earlier in the theory of critical phenomena. Having said that, I decided I should back that up, so I looked on Google Scholar under Hubbard model, and I found there were 587,000 articles. And under TJ model, there were over 3 million articles. And that seemed very impressive. And even more impressive was that the most relevant, I don't know just what that means, but the most relevant article was one by me. However, then I made the mistake of looking up the most recent article, and it turned out that TJ model was not quite what I had in mind. So in fact, if I refined the search to include the exact phrase, the number of citations to the Hubbard model went down to 50,000. Nonetheless, that's a lot of papers. I think that documents that this is a paradigmatic model. And moreover, what I think is striking a posteriori is that when we look at true solutions of the model, that is to say, not stories we've told about the model, but when we've really finally succeeded in making declarative statements about how this absurdly simple model behaves, that we find behaviors that, with remarkable consistency, predict the behaviors of, for instance, the cuprates and other highly correlated electron systems. Now, in trying to solve the model in a controlled way, there are two things we could do. We can do theory, but theory requires a small parameter, and we can do numerical experiments. And these are complementary in the sense that if there's a small parameter, there's probably some emergent long-length scale, and an emergent long-length scale will make it extremely difficult to solve the problem numerically. And on the other hand, if there are no small parameters, so we can't solve the problem theoretically, then probably all length scales are of order 1, and that's precisely where numerical studies will be most effective. All right, so here's the phase diagram of the Hubbard model at 0 temperature. For instance, I'm thinking about it on the square lattice. Here is U in units of the hopping. Here's the electron density per site. Up here is U equals infinity. Down here is U equals 0. For the undoped system, in this case, we really pretty much understand everything. It's an antiferromagnetic insulator. At small u, this is well described by some sort of Hartree-Fock description. It's a spin density wave insulator. At high u, it's a Mott insulator and a Heisenberg antiferromagnet. And now the various places where we can hope to do theory is when u is small, the weak coupling limit; when u is large, the strong coupling limit; when the density of doped holes is small, and when the density of electrons is small. This is less interesting, so I'm not going to talk about that today. Of course, for real physics, we're most interested in the hardest to understand region of intermediate couplings and intermediate dopings. Okay, so let me start by discussing the solution of this problem in the small u limit. This has been looked at in various different ways by many people over many years. I'm going to take a particular pass through the problem that was worked out in this paper with Sri Raghu and Doug Scalapino. Many other people who've reached very similar conclusions in different ways. And so in this case, we have a small parameter which allows us to treat the problem using a perturbative renormalization group fixed point, perturbative about the Fermi liquid fixed point. The basic diagrams involved were understood very long ago by Kohn and Luttinger, but this is a somewhat different view on the same thing, and in particular, an understanding that using these methods, one can get results that are asymptotically exact in the small u limit. The other new insight here is that the underlying band structure turns out to play a very crucial role in the solution, and the Fermi surface singularities turn out to play actually much less of a role than had been anticipated. Okay, so what you get out of this is that you generically find an unconventional superconducting ground state with a low Tc, and one can compute the Tc in an asymptotic expansion in U, where the leading term in lambda is of order U squared, and then there are corrections. And from the knowledge of whatever the band structure is, you can actually calculate exactly what the first two coefficients are in this asymptotic expansion. You can also calculate what the symmetry and structure of the gap function and the pair wave functions are. And so for the square lattice Hubbard model, at small u, what you find is near half filling, you get a dx squared minus y squared superconducting state, and then at higher doping, you get other superconducting states with a first order phase transition separating them. There is a small region where antiferromagnetism is important, right near half filling, but this region becomes exponentially narrow as u goes to 0. So from the perspective of weak coupling, this is a caveat that deals with a set of measure 0 of the phase diagram. Okay, so in the small u limit of the Hubbard model, first let me tell you what interesting things do not happen. There are no density wave states. There are no insulating states. There are no competing orders or spin liquids of any flavor. There are no non-Fermi liquids or marginal Fermi liquids or nearly antiferromagnetic Fermi liquids or bad Fermi liquids. And all the phase transitions you find are first order, so there's not even anything interesting quantum critical. On the other hand, you do find generically unconventional superconducting states. And this certainly establishes a few points of principle. The first is that superconductivity that originates directly from repulsive interactions without need for any attractive interactions is possible. And the second is that in this limit, there is certainly no boson that's exchanged. This is a direct result of the Coulomb interactions. There's no well-defined pairing glue. More practically, I mean, this is a theory of an extraordinarily low Tc, but you can imagine extrapolating the results to intermediate coupling, where you lose control, but you might be hopeful that the solution is continuous. And in this way, you can at least predict what you think the symmetry of the superconducting state will be. And this procedure turns out to be remarkably successful. In fact, more or less this sort of reasoning, not formulated in exactly the way that I did, but was used by theorists before there was any evidence of D-wave superconductivity in the cuprates to predict D-wave superconductivity in the Hubbard model near half filling. And similar conclusions were reached from other perspectives soon after that. And the same sort of reasoning was applied by Igor Mazin and collaborators soon after the discovery of the iron superconductors to predict that they should be S plus minus superconductors. I think the final word hasn't been said on that, but I think most people think that that's likely a correct prediction that comes from this perspective as well. Okay, so in the small u limit, what we get is generically unconventional superconducting phases. Now, what about the large U limit? Well, that actually turns out to be a limit that, as of yet, we can't treat analytically, but it turns out to be susceptible to very compelling numerical solution. We've looked at DMRG results on 2, 3, 4, 5, 6, and 8-leg ladders, and the answers look the same independent of the width of the ladder. These are very long ladders of varying widths, so extrapolating something that doesn't depend on the width to the limit of infinite width is sort of a no-brainer. There are also some recent rigorous results that support at least some of the conclusions that were reached here. So the numerics were done by Lee et al., and the rigorous results were done by a different Lee et al. And so what you find in this limit is two things. You find ferromagnetism. That's actually sort of a relief. The Hubbard model was invented as a model of ferromagnetism, and now it turns out it actually does have a ferromagnetic phase. And interestingly, there is an insulating density wave phase. Let me fill in the phase diagram. Up here at large U, there's a region of fully polarized ferromagnetic metal. This is called a half-metallic ferromagnet. At doping concentration 1/4, there's a commensurate insulating phase with both charge density wave and spin density wave order. And all the transitions in this region are first order. In between these, we get phase separation, for instance, between an antiferromagnetic insulator and a ferromagnetic metal. Okay, so what we find in large U limit is ferromagnetic metals, antiferromagnetic insulators, and first order phase transitions. All right, so now let's talk about the most interesting of these limits with a small parameter. What happens when you lightly dope the TJ or Hubbard models? And there are a variety of things that have been proposed: phase separation, stripes, pair density waves, D-wave superconductivity. So certainly at zero doping, we start with an antiferromagnetic insulator. And so one idea which was proposed early on by Vic Emery and me is that you couldn't dope this continuously. If you tried to dope it, the system would phase separate to some finite density metallic phase, and you would have a region of two-phase coexistence. If you started with this and then, of course, remembered that you should dress up the Hubbard model by putting in long-range Coulomb interactions, this leads to Coulomb-frustrated phase separation, which leads to the formation of stripe phases and other charge density wave phases. There are new variational calculations for intermediate J's by Misawa and Imada, which seem to support this. What was I saying? Yeah. Certainly now we've established that for high enough U over T, this phase separation occurs, and the fact that stripes are formed from Coulomb-frustrated phase separation has again been put on a rigorous basis very recently in this paper by Lieb and collaborators. So this is certainly one thing that can happen in this regime. Another thing that can happen is mesoscale phase separation, even without the long-range Coulomb interactions. For instance, this can produce stripes. This was proposed on the basis of Hartree-Fock calculations early on by Zonen and Gunnarsson early on, and others. These stripes in this case were insulating, but later in numerical studies of TJ models, White and Scalapino and others found that, in fact, metallic stripes have lower energy. And recent variational calculations that are more accurate, I think, have found similar stripes, which I'll talk about in a minute. For intermediate values of U over T, the energy differences between stripe formation and phase separation, that is to say between mesoscale and macroscopic phase separation, are very small. In the presence of Coulomb interactions, the results are more or less the same. It's probably not something that's worth fixating on too much. Let me just mention briefly the results of a variational calculation that was just posted on the internet. So this is the best variational calculation yet by the technical measure of bestness, which is that it has the lowest variational energy. It uses tensor network states. It does calculations in some range of J between 0.2 and 0.8 and some range of doped hole concentration between 0 and 16%. And what it finds is that there are 3 different broken symmetry states, all of which have almost the same energy over this whole range of parameters. There's a uniform D-wave superconducting state, which, depending upon whether x is bigger or less than some value, may or may not have coexisting antiferromagnetic order. There's a state with coexisting charge density wave, spin density wave, and uniform superconducting order. And there's a pair density wave state, which is got coexisting charge density wave, spin density wave, and Larkin-Ovchinnikov type superconducting order. Here's a picture of those states. So here's the state of uniform D-wave superconductivity. In this picture, the blue bond is supposed to represent a pair wave function with positive amplitude on this bond, and the red shows that it's got negative amplitude on that bond, and you can see that it's uniform. This state has a non-zero expectation value for the pair wave function at 0 momentum, but 0 expectation value for either charge or pair wave functions at any non-zero momenta. There's the striped superconductor, in which now the magnitude of the pair wave function is modulated in some periodic fashion. There's some modulation of the charge density as well. In this case, there's also modulation of the spin density that I'm not showing. There's a non-zero value for the 0 momentum component of the pair wave function and at various wave vectors. And finally, there's the pair density wave, in which as you can see, the phase of the superconducting order parameter changes from here to there, so that the spatial average of the superconducting order parameter is 0, but there's superconducting order at some non-zero wave vector, which is, in fact, the wave vector that's twice the wave vector of the charge density wave ordering. This turns out to have the lowest energy in the variational treatment, but its energy is only 1/100th of T per hole smaller than that of the uniform superconducting state, and 1,000th of T per hole smaller than that of the pair density wave state. And these are numbers that are both numerically not believable and physically equivalent to 0. There are a couple of other things to note about this. First, the charge density wave order in this case is totally unrelated to Fermi surface nesting, holding the density of holes fixed and holding the band structure fixed. As you change the ratio of J over T, the periodicity of the charge density wave order changes. It's a strong coupling effect. The pairing and the vertical stripe formation are linked with each other. The local order looks the same and develops coincidentally. On the other hand, the charge density wave order enormously reduces the superfluid stiffness of the system. In fact, the degeneracy between these two states can be recast as a 0 superfluid density in this direction. And this pair density wave state is phenomenologically interesting. There's some experiment that is reviewed in this paper of Eresberg and Eduardo Fratkin and John Tranquata and mine, that this state has been seen at least in lanthanum, barium, copper oxide, and maybe in other high-temperature superconductors. Okay, good. So that's what we find in the small doping regime. We have a phase diagram now as complete as I can give. In this region, depending on details, we're going to get striped superconductors, pair density waves, antiferromagnetic superconductors, uniform superconductors, pneumatic superconductors, and phase separation. It's remarkable. This is a stupid, simple paradigmatic model. It's not a model of the Coop rates, and yet the detailed nature of the antiferromagnetism, the D-wave superconductivity, the highly conducting and even superconducting stripes, and the pair density wave and pneumatic phases all come out of these things. Can I take a minute more since other people did? Okay, so let me skip critical points. That's interesting, but let me just conclude with one visionary statement. So there's recently been some interest in a new hydrodynamic approach to studying the properties of correlated electron systems at non-zero temperatures. There were, for instance, these two very interesting papers that appeared on the web. And what this is an attempt to address really the most vexing problem in the theory of strongly correlated systems, which is the nature of this bad, strange, marginal metallic behavior that Laura talked about in her talk. And the idea behind these hydrodynamic approaches is that where interactions are small, so quasi-particle lifetimes are going to be short, maybe even so short that the quasi-particle notion ceases to be well-defined, what is left? And what could be left is a generalized hydrodynamic description in which the system relaxes very rapidly, leaving behind only a smaller number of slowly relaxing, almost conserved variables. And that then one can give a hydrodynamic description in terms of these slow variables. And now, just to show you how radical those words are, in a Boltzmann transport regime, if I were to calculate the resistivity, we would find that it was proportional to the quasi-particle scattering rate, 1 over tau. Now, in a hydrodynamic description, we would probably find that the resistivity was proportional to the viscosity of our fluid. And if a kinetic theory is possible for our fluid, we would find that the viscosity of our fluid was proportional to the quasi-particle mean free path, hence proportional to the quasi-particle lifetime. So we would find a resistivity that was not inversely proportional to the quasi-particle lifetime, but proportional to the quasi-particle lifetime. All right, so there we go. Thank you.
So thanks, Steve, for that beautiful map of the Hubbard model. Not quite filled out yet, but largely so. We have time for some questions. If there are any, please come to the microphone. So I guess in the absence of any at the moment, I'll ask a question of just intuition. So you gave a variety of kind of somewhat controlled approaches and maybe some little bit less controlled in the middle to arrive at least a fairly a picture that these kind of striped states were very common. Mm-hmm. What I didn't get so much was an intuition for why that would be, and why so many states would be so competitive in energy.
Okay, so I do have an intuition about this. The results seem much more striking than the intuition. But the intuition somehow is the intuition that if we have an antiferromagnetic insulator, the motion of doped holes in there is highly frustrated. And so rather than the system making a compromise between electron itineracy and antiferromagnetism, it's better for it to be antiferromagnetic in some portions of space and to be itinerant in other portions of space. So this could either lead to phase separation macroscopically or mesoscopically, that within the stripe you've destroyed antiferromagnetism, the holes can delocalize. If the delocalized holes want to form D-wave pairs, then that occurs simultaneously, which it seems to do. So, and in fact, the striped phases found in these variational calculations have strong antiferromagnetism between the stripes. So they clearly are doing this drama of expelling the holes from the antiferromagnetic regions. Now, why these different symmetry phases come out to be so absurdly close, and why that's so robust over a range of parameters, I think is totally mysterious. The only other thing I can say about that is that I think there's every evidence that the real materials do this too, that we have all these different orders and their transition temperatures are all just about the same. And so perturbing the system a little allows you to tip the system from one phase to another phase that looks entirely different. And so it seems to be an essential feature of this strong correlation problem that there are multiple phases in very close competition with each other.
Very good. So we have a few questions from the audience now, please.
So Steve, in talking about these different nearly degenerate phases, the word pseudo-gap didn't appear in your talk? What does that mean?
Right. So first place, in the limits where I can really control the calculation, namely in the weak coupling limit, there's no pseudo-gap. In the strong coupling limit, we have these different phases that are competitive with each other. I believe that part of the answer to Leon's question is that locally we have strong pairing correlations. And those strong pairing correlations are the same in all these different phases. Now, given that they're the same in all these different phases, it means they're very small energies that allow us to fluctuate and probably destroy the long-range order. But this local pairing, which, you know, if you put me against the wall and say, do I know that it's superconducting pairing and not charge density wave pairing, I probably can't tell you. But some form of pairing is a very robust and very local feature, and that, I believe, is the essence of the pseudo-gap. But that's a belief. That's not a calculation.
Another question over there.
So my question is of a sort of a meta-theoretical nature. So you said early on that to do controlled theory you need a small parameter, but in fact what you described is controlled theory only for the weak coupling case. So I guess my question is there something that tells you, is there a general sort of rule for what sorts of small parameters can be used to actually attack these problems? Or is it just that the only problem we can really solve is free electrons?
No, look, so the one small parameter that I didn't talk about is that if you're near a quantum critical point, then deviation from the quantum critical point is a legitimate small parameter. It allows you to describe the system independent of its details from a quantum field theory point of view, and then up to your ability to solve a quantum field theory, you may be able to say something using a much more non-trivial small parameter. But look, at the end of the day, a small parameter is useful if somebody figures out how to use it.
On that interesting bit of linguistics and meta theory, let's thank Steve again.